pin number 40, just now I mentioned that it is a supply connection pin where plus 5 volt power supply is connected. Other plus 5 volt power supply is connected in between pin number 40 and 20. We have already discussed the on-chip data memory, which is of size 128 bytes. We have seen its 3 partitions. Now we'll see the special function registers. The special function registers and their addresses are as shown in this figure. The 8051 operation that do not use the internal 128 byte addresses from 00H to 7FH are done by a group of registers called as special function registers. These are accessed by addresses 80H to FFH or with their functional names. As shown here, you can observe the addresses are in the range from 80 through FFH. Even though there are 128 memory locations intended to be occupied by them, there are only 21 such registers. Rest of the locations are intentionally left unoccupied in order to enable the manufacturers for further development. Here you can see here is a vacant location as well. This portion, all these are vacant locations, and those are kept aside by the manufacturer for further development. Attempting to use an address that is not defined produces unpredictable result. Suppose I go for attempting the memory location with the address C0 or C8 or E8 or F8 or any location here, then it is going to obviously produce unpredictable result. Some SFRs which are marked with start, those are bit addressable also. We have seen the programming model of 8051, and over there we have seen the list of SFRs, and certain SFRs were marked with star, and those are nothing but the bit addressable registers or bit addressable special function registers. All the SFRs are tabulated here. You can see the first column is the name of the register. The function of 8 is specified in the second column, and the internal RAM address in hex is provided in the third column. So, for example, register A, the function of 8 is accumulator, and its address in hex is 0E0H. Likewise, all the special function registers are mentioned in this table. We'll see all these special function registers in detail one by one. Very first is the register A, which is also known as accumulator. Register A is a general purpose register used for storing intermediate results obtained during operation. Prior to executing an instruction upon any number or operand, it is necessary to store it in the accumulator first. All results obtained from arithmetic operations performed by the ALU are stored in the accumulator. Data to be moved from one register to another must go through the accumulator. In other words, the A register is the most commonly used register, and it is impossible to imagine a microcontroller without it. More than half of the instructions used by 8051 microcontroller use somehow the accumulator. The accumulator is of size 8 bits. This is the bit 0 of accumulator, and this is the bit 7. That is nothing but the most significant bit of the accumulator. So it is the one of the most important register of 8051. Then another register is B register. It is also a general purpose register. Multiplication and division can be performed only upon numbers stored in the A and B registers. All other instructions in the program can use this register as a spare accumulator. So here it is shown, this is the bit 0 for B register, and this is the bit 7 for B register. So it is a 8-bit register. Then comes the data pointer, which is abbreviated as DPTR. It is a 16-bit register used to hold the address of a byte in memory. As shown in figure, it is made up of two 8-bit registers, that is DPH and DPL. Together they form the DPTR of size 16-bit. DPH and DPL both are of size 8-bit and which are having the bitmap from bit 0 to bit 7 respectively. It is used in internal and external code access and external data access. Next comes the program status word, that is PSW. PSW register is one of the most important SFRs. It contains 4 math flags which are carry, auxiliary carry, overflow and parity. It also contains 2 register bank select bits and 1 user definable status flag. You can see the bit 0 of PSW is P, which is nothing but the parity flag. This flag is set to 1 whenever it is the odd parity of the accumulator. The meaning is that whenever the content of the accumulator consists of odd number of ones, at that time this flag is set. Bit 1 as shown here is not used by 8051. Rather, it is intended to be used in the future versions of the microcontroller. Then it is the overflow flag. Bit 2 is the overflow flag, which is set to 1 whenever the signed arithmetic is performed. After performing the signed arithmetic, if the result is too large to fit into the destination, then this flag is set. As shown, the next 2 bits are RS1 and RS0. Those are nothing but the register bank select bits. These 2 bits are used to select one of the 4 register banks of RAM. We have already seen the structure of RAM, and in that we have seen that there are 4 banks of the registers. The names of the banks are register bank 0, register bank 1, register bank 2 and register bank 3. One of these register bank is selected at a time, and the 2 bits, that is bit 3 and bit 4 of the program status word is going to select a particular bank at a time. The selection is based on this table. Whenever the RS1 RS0 combination is 00, at that time the bank 0 is selected, that is the address in the range 00 to 07H of the RAM is active. Whenever the combination is 01, at that time bank 1 is selected. For 10 combination, bank 2 is selected, and for 11 combination, bank 3 is selected. Upon reset, automatically bank 0 is selected. That is, the RS1 and RS0 bits in the PSW is having the status 00 upon reset. Then comes the bit number 5, which is the F0 flag. It is a general purpose user flag that can be set or reset by the programmer to record certain events. Whenever user want to record certain event like the lamp is on, the motor is off, this 1-bit information can be stored at this flag, which is the part of PSW. Bit 5 can be set or reset to indicate a particular event. Then comes bit number 6, which is the auxiliary carry flag. The auxiliary carry flag is normally used in the BCD operations. This flag will be set whenever there is transfer of carry from the bit position 3 to the bit position 4. And the most significant bit of the PSW is the carry flag. The carry flag is set whenever there is a carry or borrow generated out of bit 7. So while performing the addition operation, when there is carry out of bit 7, as well while performing the subtraction operation, when there is borrow out of bit 7, the carry flag is set. This is the 8-bit program status word register. Then comes the another important register, which is SP, which is nothing but stack pointer. The stack pointer is also a 8-bit register, which is used by 8051 to hold an internal RAM address, which is called as top of the stack. It is the address of the location where the last byte of data was stored by the stack operation. When the data is to be placed on the stack, the SP increments before storing the data on the stack. Thus, the stack grows up as data is stored. Similarly, when the data is retrieved from the stack, the byte is read first and then the SP decrements to point to the next available byte of stored data. The stack operation is shown here with a simple diagram. Initially, assume that the content of SP is 07. Now, I want to carry out the store data operation. So, whenever I write the data on the stack memory, at that time the stack pointer is incremented first and the first byte of the data to be stored will get stored at the location 08H. Similarly, with the next write operation on stack memory, the stack pointer goes to 09 and over there the data is next byte of the data is stored. If the third byte of data is to be stored, again the stack pointer is incremented so that it will become 0AH and over there the data will be stored. While the retrieve operation is performed, whatever is the current content of SP, that is 0AH, at that location whatever is the content is retrieved first and then the stack pointer is decremented by 1 so that now it will point to the location 09H. With the second retrieve, the data is first copied and then the stack pointer is decremented so that it will become 08H. With the third retrieve, the data is copied and then the stack pointer will become 07H.